Hello, everyone. I guess it's time. Close enough to time. Everyone, I'm here to introduce a legend in the networking industry. The man who personifies the name Gerbil. The man who is humble beyond all else. A man who has helped out the industry in ways that are uncountable and innumerous. He wrote the pairing DB, as crappy as it is, but we will be making that better soon. But he wrote it, and he made it what it is today. He owns the coupon.net site, which I'm sure all of you go to every day, and if you don't, you should be. But most important of all, today, this very day, Richard Steenbergen is turning 31 years old. Let's all have a round of applause. And now he's going to teach us about optics and networking, or something. I don't know. I'll have fun. Bye-bye.
Hello. So, let's take your water. Everything you always wanted to know about optics but were afraid to ask, except that doesn't apply to Patrick because he's never afraid to ask anything. So, the purpose of this tutorial, I wanted to talk about optical networking for an industry that is largely based around fiber technology, and yet at the same time, a lot of router people really don't have that much experience working with fiber. There's a lot of misconceptions out there. There's a lot of confusion. I've had people ask a lot of questions. I've seen a lot of questions on mailing lists and things like that. So I wanted to go back and compile all of the frequently asked questions people ask about optical networking, what you can do, what you can't do, and just kind of touch on at least the basics and in some cases some details of a lot of the fundamental topics behind it. So. Will this presentation make you an optical engineer? Probably not. Realistically, if you were to learn everything that's in this presentation, you would be. But we're not going to touch on every last detail of everything. But it should give people the basics to understand a lot of things. So hopefully it's good. So start with the very basics. What is fiber? How does it work? Fiber is basically a waveguide for light. It works on a physics principle called total internal reflection. And the way this works is the cables are actually composed of two layers. There's the core and there's the cladding that goes around that. And the cladding has a higher index of refraction than the core. And the way this works in physics is when light tries to go from one medium to another and it tries to go into a higher index of refraction, if it's below a certain angle, it gets reflected back in. And so having the core wrapped by the cladding keeps it from leaving the core. It keeps the light injected back into the core. And the only way it can propagate is through the fiber and out. So here's the stolen Wikipedia diagram of how that works. You have an acceptance cone that is set by the certain angle that you can take light in. And if you try to send light from outside that angle, it doesn't make it through. But as long as you stay within that certain angle, the light will always be reflected inside the core. Gratuitous image from Wikipedia, someone's laser pointer and an acrylic bar, and it shows how that works. So kind of the insides of a single mode fiber. In theory, this is to scale, but it's more stolen Wikipedia images. So this shows kind of the relative sizes, and this is the inner part of a fiber. And then when you have like a patch cord, there might be strain relief on top of that, and then an outer cable that's much thicker. But this shows the insides. Basically, what we're transmitting over fiber is digital signals that are encoded as analog points of light. Pulses of light. Today, that's primarily a method called non-return to zero. It's a very simple modulation. And we use fiber in pairs for the most part, where one side transmits and the other side receives. There's actually ways that you can transmit on a single strand, but for most systems that aren't doing anything fancy, we just use pairs. And this kind of shows an eye diagram of what the signal looks like and what the binary encoding is. Basic fiber types. At the most basic, there's the single mode fiber and a multimode fiber. And really the main difference is the core size. Multimode fiber has a very wide core. and it allows multiple modes of light to pass through. And basically, what the size has to be to allow a mode or multiple modes of light to go through is relative to what the wavelength of light is. So single mode is small enough that it only allows a single mode of light for the particular spectrum that we use it in. So some details on that. Multimode fiber basically comes in two common core sizes. One is 62.5 nanometers, micrometers, and the other is 50. Basically, multimode is designed for cheap optics. The wide core lets you use an incoherent light source, so you don't need an expensive laser that will focus the light. It accepts a large amount of light. It typically operates in the 1350 or the 850 or the 1310 bandwidths. But basically, the accepting of a lot of light and the ability to use cheap optics comes at the expense of distance. Because it's so wide, it's basically the light version of multipath interference from radio. You have multiple ways the light can travel, and so you end up with all these extra echoes and things like that, and it's called modal distortion. And it basically limits you, depending on the bandwidth and the type of fiber that you're using, it basically limits you to somewhere between tens to hundreds of meters. You could get longer with like really low speed optics, but it's limiting. And there's also a recently introduced standard called OM3, which if you see it in data centers, it has aqua colored cables instead of orange. And basically it's laser optimized. It's designed to work with the new 10 gig lasers and go up to 300 meters and do much better than the older standards. Single mode fiber, by comparison, has a much smaller core. It's typically somewhere between 8 to 10 microns. And because of that, single mode supports distances up to several thousand kilometers with appropriate amplification, dispersion compensation, which you get more into. The downside, obviously, is that it requires more expensive lasers. And they typically operate in the range of 1270 to 1625, and that may vary by a few nanometers here or there, but that's pretty much the bandwidth that's covered by all the lasers. And there's classic single mode fiber, which is called SMF28. It's actually a product name, not a standard name, but there's a lot of specialty fibers that go along with that. There's low water peak fiber, there's dispersion shifted fiber, there's non-zero dispersion shifted fiber. There's a lot of specialty single mode fibers. So back to this diagram, this shows the multiple paths that light can travel inside the fiber, and at the end you end up with a lot of signals that have traveled different paths at different lengths, and so you get a lot of dispersion, distortion, and that's distance limiting. Another thing that you can do with multimode and single mode fibers is when you jumper them together, what happens? You have a very narrow laser coming from a single mode fiber going into a very wide situation. And basically what happens there is it still gets bounced around. But if you can actually improve, if you have some multimode plant, you can improve the characteristics by using a mode conditioning cable. And basically all that is a manufactured fusion splice that sets the offset between the single mode and the multimode. So you want it to hit it at a certain way, at a certain angle, that minimizes the reflections inside all the multipath reflections inside the multimode, and lets you get longer distances. So here's kind of a size comparison, and something happened to my picture and it got cut off on the bottom there, but just kind of showing old LED transmitting the modern vertical cavity surface emitting lasers, which you might see in like a old Gigi SX, that kind of thing, and then anything that's an actual laser, which would be long haul single mode optics. It kind of gives you a size comparison of what width signal you're sending. So a lot of times people ask me, what happens when you do this? What happens when you send an LED source or a very wide source down different types of fibers. And what happens is when you send a wide signal down a narrow path, basically you can't fit the light. The fiber is not wide enough to accept it. And so you just end up discarding 90% of the light. You might be able to use it for a couple of meters, but that's about it. On the other hand, you can send a laser source down a very wide path. And the only thing that happens there is it kind of bounces around, right? So you get the same. You're limited by the modal reflections, but you're still able to pass a signal. And as a rule of thumb, it will always go at least as far as the wide signal, sometimes further. But if you really want to achieve maximum distance, you need a laser source and a single mode fiber, and that's more expensive, but that's really what you need to do anything good. I didn't want to touch on pluggable transceivers in here because it's already been discussed at length. There were two presentations, one back in October 2003 on 1 gig stuff, GBICs and SFPs, and then one that I did back in February 2008 on 10 gig pluggable technology, and you can see the URLs. Some updates coming at this from 2 years later, some changes from when this was written. SFP Plus is now shipping in large quantities. The prices are actually not bad. I was pretty down on SFP Plus, but they've managed to make the prices pretty reasonable. And they're also, at the time, they were only shipping SR. They're now shipping LR, so you can now get 10-kilometer reach. They're now shipping LRM, which is a long-reach multimode standard that lets you get 300 meters on old fiber. And like I said, they're reasonably cheap. Turns out that they do have longer reach optics in the pipeline. You can't order them from your router vendors yet, but you can find them on like random no-name Chinese vendor websites. And they're in the pipeline for coming to Cisco and Juniper and things like that. There's no DWDM yet. No one's done that, but there's actually some people advertising CWDM, 40-kilometer SFP plus. No clue on what the price is yet. I couldn't find a way to order them without calling China, but they're coming. And basically, it leaves SFP Plus as the format of choice for the new high-grade enterprise boxes. So you're not going to see it on your carrier boxes where you need to do DWDM, but you're going to see it in your enterprise-grade boxes where you might be given a 32 or a 48-port 10-gig blade and want to populate it with optics that cost a couple $100, not a couple thousand. Like I said, still not a complete replacement for XFP, but it's making progress and it is cheap. So a bunch of optical networking terms, concepts, things to go into. First question is people talk about optical power. What is optical power? Optical power is simply the brightness or the intensity of the light. And what happens is as the light travels through fiber, some of the energy is naturally lost. Some of it is absorbed by the glass particles, converted from light to heat. Some of it's scattered. But as you transmit light through fiber, some of it's going to be naturally lost, and that process is called attenuation. We measure optical power in decibels. So a decibel is 1/10 of a bell, and it's a logarithmic scale unit for expressing a relationship between two values. It's what's called a dimensionless unit. It doesn't represent a physical quantity. It's purely a math concept. It represents the difference between two other quantities. So, like I said, the rough estimate that people use is a 3 dB change is a half, minus 3 dB change. I'm sorry, a 3 dB change is double, a minus 3 dB change is half. That's actually rounded really close. The actual scale is based on 10, so a 10 dB change is 10 times the signal, but it just so happens that 3 dB is double, so people latch onto that as a concept. If you want to express an absolute value of light, you need to compare it to a known reference value. And that's where you see dB and then some letter come after that. In optical networking, we use the DWDM, which is decibels relative to 1 milliwatt of power. In wireless networking, you might see dBi, you might see various other things, but it's the same concept. So 0 dBm is 1 milliwatt of power, 3 dBm is 2 milliwatts, minus 3 dB is half a milliwatt. And people have asked what's an actual no signal, and that's negative infinity dBm. There's been some cases where vendors have when you have power readings DOM built into your optics and you have 0 power, they report 0 dBm, and that's actually a really strong signal. So the correct way to express no signal at all is negative infinity dBm. Confusion between the two is actually one of the biggest problems that I run across when working with data center techs, testing fiber, things like that. People don't understand there's 2 ways of looking at this. So you really want to know what you're talking about, whether you're talking about a relative change or whether you're talking about an absolute power reading. So why do we measure light with a decibel? Well, basically because light, like sound, same reason we use decibel to measure sound, follows the inverse square law, which means for every unit of distance separating the sender and the receiver, you lose that distance squared worth of power. So in this example, signal travels distance x and it loses half of its intensity. It travels another distance x, it loses another half. The amount of loss is relative to the amount of power that was put into the system to begin with. So after distance 2x, you're down to 25% power. After distance 3x, you're down to 12.5% power. And the reason that we use a logarithmic scale is that basically cancels that out. It turns it back into a simple addition problem where you say a 3 dB change is half or double of the signal. So now you say it's 3 dB per distance x. So if you go distance 2x, you can add it. It's another 3D. It's another 3 dB. It's another 3 dB. And it makes the math much simpler. That's basically why we use it. So I threw in a table that I stole from somewhere that shows the amount of power. And you can see that by the time you get down to any amount of dB loss, you're down to very, very small fractions of the original power. You start quickly falling off. Other major concept to deal with in optical networking is dispersion. Dispersion just simply means to spread out. There's various causes for this in optical networking, but basically the problem is it degrades the signal. The 2 main types of dispersion that we have to deal with, there's also modal dispersion that we talked about in multimode, but we won't really have to calculate that. The 2 kinds that we primarily have to deal with are chromatic dispersion, which is different frequencies of light propagate through a non-vacuum medium at different speeds. And so when you transmit a signal, the signal can't just be an instantaneous piece of spectrum. It covers some amount of spectrum. And so because the one part of the spectrum may travel faster than the other part of the spectrum, by the time it travels some length of distance, the signal has now spread out quite a bit and it's hard to read. The other kind is called polarization mode dispersion. And basically what happens there is it's what happens when the fiber is not perfectly round. Light has polarizations. That's how your sunglasses work. You try to block out the horizontal polarization, which is light reflecting off the ground and giving you glare. You try to only focus on the vertical. It's the same thing. Light travels through different polarizations. And because the fiber may not be perfectly round, you may have one polarization of light that gets there faster than the other. And so that also causes some problems. Chromatic dispersion is definitely the worst. It's basically chromatic dispersion is the limiting factor in optical networking for the most part because attenuation you can deal with amplification, but chromatic dispersion is the engineering limit that most people deal with. Polarization dispersion is especially bad on old fiber. Modern fibers are manufactured better. So here's kind of a diagram showing the effects of the dispersion. Where before you had 3 clearly distinguishable pulses where you could see peak of the signal is 1 and the signal off is 0. As the signals are spread out, you can no longer tell what's a 1 and what's a 0. And that's basically what you're fighting against. There's several frequency windows that are optimal to transmit into fiber. The first one's called 850 nanometer, which is the first window. It was the first window that people used in fiber optic systems. It has very high attenuation, and so you really only see it for very short reach applications today. Probably the longest that you'll see it anywhere today is 300 meters. But it was the cheapest and easiest laser to build, so people started using that. The second window is the 1310 window. The reason this is important is it's the point of zero dispersion for classic SMF, the fiber that people originally deployed back in the 80s, early 90s. It has higher attenuation than, not higher than 850, but it's not the lowest point of attenuation, but it's the lowest point of dispersion. And today people use it for medium reach applications, and it's called the O band. O stands for original, for whatever that means. The third window is the 1550 window. And there's a band around that called C band, stands for conventional band. It covers 1525 to 1565. This is basically the lowest point of attenuation over single mode fiber. So if you want to go the maximum distance, you need 1550. The difference between 1310 and 1550 on modern fiber is not quite a half the rate of attenuation on 1550, but it's pretty close. And basically, C-band is the bandwidth, the range that's used for all long reach and DWDM today. And there's a fourth window called the L-band, or long band. You'll principally only find that used in Japan. The reason for that we'll get into more later, but it turned out they deployed a type of fiber that later they found out to have problems, and the only way to work around that was to use a different frequency than most other networks use. So they shifted to a higher band. So here's kind of a diagram that I saw from someone somewhere that shows kind of the progression of fiber technology. You can see the early 80s fiber, there were very clear reasons why you had to pick certain frequency ranges. There's a limitation called water peak. What happens when they manufacture the fiber is, I think I'd probably talk about that somewhere else. I got my slides swapped around, but what happens is there's a manufacturing process problem where you get water, you get hydroxyls in the glass that you can't get out, and the water absorbs specific frequencies of light. And you can see that there's what's called water peak, these big peaks where the spectrum's completely unusable because of how much it absorbs. And you can see as they've progressed through fiber technology, they make low water peak fiber now that has very little issues. It works basically like the most optimal bands, but this shows kind of the relative positions of the bands and why they were chosen. There's a concept now that's becoming more and more popular called forward error correction. What this is you add extra redundant information to your transmission so that if there's an error, you can recover it computationally. So you can kind of think of it like RAID 5 for your packets. Even if you lose a hard drive, even if you lose data, there's enough other data in the redundant information that you can rebuild it computationally. And the way that it works is it extends the receiver sensitivity. So where you might have a receiver that was taking, might be losing one out of 1,000 packets, it might be losing, 10 to the -4 or -3 worth of signal that would be completely unacceptable. Because of this, it's now able to recover almost all of those, and it takes your bit error rate down to something that's acceptable. And so you can get much longer distances out of it. And there's been a couple different algorithms out there, but basically what you're doing is you're using clever math, and you may pad the signal by 7%, and it may give you a pretty significant distance increase and a lower bit error rate at the same time. And the way that this is typically implemented on a packet or frame is as a digital wrapper. It's called G709, which we'll talk about more later. Here's kind of a diagram showing the uncoded bit error rate relative to the signal to noise ratio and showing the improvements between the original effect standard, the G709 effect standard, and then the latest one, or EFEC, and then the latest one, which is the blue line, which shows there's really significant improvements by adding a very small amount of overhead to your data. You get much better signal to noise ratio, bit error rates. So G709 is what's called the OTN, digital wrapper. OTN stands for Optical Transport Network. It's a set of standards that allows interoperability from an optical transport perspective across an optical network. Why do you need this? Basically, it's so the optical network is completely transparent. The way that wavelengths used to be implemented in the past, for example, I might get a 10 gig wave from a provider, but they're expecting me to speak OC192. And so their endpoint looks at my OC192 frames. It needs me to speak OC192 frames or STEM64 or whatever the case may be. It needs to understand my framing. It needs to look at my framing. It needs to modify my framing. So it's not completely transparent. You're not actually selling someone a wave. You're selling them a transport service over a wave. So the OTN lets you get that level of transparency. And the other big thing that it lets you do, some protocols just aren't as good as troubleshooting as others. For example, we do a lot of Ethernet. You might buy waves today and use them as purely 10 gigabit Ethernet because the interfaces are cheaper. But Ethernet's not a very good protocol for working on the LAN. It wasn't meant to do that. So, you know, we've all had anyone that's had an experience calling your transport provider, and you say my 10 gig E circuit's down, and they say, what alarms are you seeing? And you say, I don't have alarms, it's Ethernet, and they laugh at you and hang up. That's basically the problem that you face. You need some level of diagnostic information. So by taking whatever protocol you want to send, by taking, be it frame relay, SONET, ATM, Ethernet, IP, whatever, by taking that and encoding it in a standard frame that the transport gear uses, you can now have the transport gear handle all the diagnostics. So you don't need involvement from the customer. You don't need all that complication. And the other thing that you can do with it is you can do optical multiplexing. So we're kind of like SONET, where you might take 4 OC48s and mux them into an OC192. You can take 4 10 gig signals and mux them into a 40 gig signal. And this is the framing that lets you do that optically for whatever you want to transport. Get into wave division multiplexing. Everyone knows that light comes in different colors. What you do with wave division multiplexing is you combine different signals of different colors onto the same fiber, and the goal is to have them not interfere with each other in any way. So you have a mux that takes in multiple wavelengths, use the symbol lambda for wavelengths, and combine them onto a single fiber, and you might have a power graph that looks like this, where you have all these individual peaks that are nicely separated, don't touch anything, and you have 100 gigahertz spacing between them, and the signals don't interfere with each other. It's the perfect world. You increase capacity as much as you want over a single fiber. There's multiple types of WDM. The most common are what's called dense and coarse. Basically, they do the same thing in the exact same way. The only difference is the channel spacing and the range of optical spectrum that they cover. So here's kind of a graph showing a CWDM, a coarse wavelength spacing versus what's basically now 10-year-old DWDM, and the modern stuff is much smaller than this, but it shows the relative difference in signal spectrum size. So CWDM, or coarse wavelength division multiplexing, basically is loosely used to mean anything that's not DWDM. The most popular meaning for people is 8 channels with 20 nanometer spacing, centered on 1470, 1490, 1510. And here's kind of a graph showing the way the filters kind of overlap each other. With low water peak fiber, there's another 10 channels that are available that are standardized. So in theory, you can get up to 18 channels. The difference is because these cover a very huge amount of spectrum, the optical properties are very different. So you may see much more attenuation on your low channels than your high channels. People also use CWDM to refer to just a 1310, 1550 mux, which is just a simple, very wide 2-band mux. DWDM is a much more tightly packed system. Basically, any long-haul system, anything that's a commercial system, you're going to see is DWDM. And DWDM is basically based around the C-band. The channel sizes are standardized. There's what's called an ITU grid that defines what the channels are, what the spacing is, what the exact offset is. There's a few different popular grid sizes. There's the old 200 gigahertz spectrum, which was you got 20 channels out of C-band. There's 100 gigahertz, which you get 40. And the new modern technologies, 50 and 25, you can get up to 160 channels within C-band. Basically, 200 gigahertz is old, like pre-2000 era technology that there's no call for anyone to use anymore. 100 gigahertz has basically been where it's at for all the cheap systems, pluggable systems, passive muxes, things like that for many years. And anytime you buy an expensive modern commercial system, you're basically, for the last few years, have been getting a 50 or a 25 gigahertz spacing system. So you can get up to 160 channels. So what are the advantages? CWDM, because the bands are really wide, less precise, cheaper, less precise lasers can be used. It's not that the signal is 20 nanometers wide. The signal is about the same size. It's that the lasers vary over their lifespan as they warm up, as they cool down. You might see the signal spread quite a bit. And you can use cheaper uncooled lasers, which will always fit in that very large window. And so it's cheaper to implement, cheaper to sell. And if you only need a few channels, it might work for you. DWDM, obviously, you get a lot more channels. 160 channels and 32 nanometers of spectrum versus 8 channels and 160. It's a huge improvement. But the big part is that it stays completely within C-band. And the reason you want to do that is that's where attenuation and dispersion are the lowest. That's where fiber amplifiers work the best. And that's where dispersion compensation can be applied. So you really only see CWDM systems on an unamplified, very simple network, point-to-point. Anytime you do anything fancy, long haul, rings, add drop, anything fancy, you're talking about DWDM. Here's another graph showing kind of 3 popular progressions from 200 to 100 to 50 gigahertz spacing and how they fit inside a CWDM channel. So you see you get a lot more signal. There's other meanings behind WDM, other uses. One that you see a lot is 10 gig base LX4. What they did was, in order to implement a 10 gig signal over older fibers, they did the mux inside the transceiver. So you transmit 4 wavelengths over, it's a non-standard channel spacing. You're supposed to use this over a clean dark fiber. But by using 4 different wavelengths that are around the 1310 spectrum, you can run this over multimode and get 300 meter reaches where before you couldn't do that at all at 10 gig. And if you run it over single mode, you get the same. You get 10 kilometer. You get the same type of reaches you would expect to see from an LR type optic. Expect to see a lot more of this in 40 and 100 gig as these technologies evolve. Basically, because there is no optical 100 gig at all outside of the lab, and optical 40 gig is difficult. And at the moment, it's cheaper to implement it. In a lot of cases, it's cheaper to implement it with a 4x 10 gig signal than it is with a native 40 gig signal. The other common use you might see is the 1310, 1550 mux, and people will use that just to turn 2 cross connects into one or do whatever. And then the other I should say 1,000. I'm so used to 10G. The other way you might see that is with BX optics, which is what some vendors sell, where they have a 1310, 1550-ish type mux built into the transceiver, and so you can use a single fiber strand and plug it into one of these optics on each end, and one side transmits 1310, the other side transmits 1490. The integrated muxes, you only need to use a single strand of fiber. So there's you might see some use of that. We'll talk about the WDM networking components out there. So the big component that you see is the Mux, Demux, which is short for multiplexer. Sometimes people call it a filter, sometimes people call it a prism. The term filter is more technically correct as to how it actually works. It filters specific colors of light and sends it sends that specific color of light out a port or accepts it from a port. It's not really a prism, but people understand the concept of a prism splitting light, and so sometimes people call it that. It's a very simple device. It combines or splits multiple colors of light onto a single fiber, which is called the common fiber. They're entirely passive devices. They require no power. Any complete system requires a mux and a demux. On most modern systems, they're the same piece of hardware, but you need both components. You need one which combines the signals from all the different spectrums, and you need one which filters it, because if you just sent the same light to every receiver, the receivers are wideband. They would see all the light, and they would see 5, 10 different signals, and they would be confused. So you need something to actually filter and split the light signal on both ends. Sometimes people ship them in a single box or a single unit, but it's really two distinct components inside for simplicity. If you're operating over a fiber pair, you need both sides on both ends. Here's kind of how a mux works. Basically, they're based around Bragg gratings, which is a mechanism that reflects a certain frequency of light and transmits other frequencies. So you see that there might be one of these engineered to reflect a certain piece of light, and you use that to do the channel splitting. The channels are actually overlapping. They're not completely isolated from each other, but what happens is you need to maintain enough channel isolation. So there might still be signal from channel 1 leaking into channel 2, but it's at such a low level that it doesn't cause interference. And basically here's the terminology broken out as far as the channel spacing is based on the center of the channel. The channel isolation is between the point of maximum signal to the point where it crosses over into the neighboring sideband. What's called the channel pass band is the width that you can actually pass before you do that. Basically the terminology behind that. Another common component is called the OADM, the Optical Add-Drop Multiplexer. And basically what this does is it selectively adds or drops certain channels while passing other channels through without disruption. So where you might see a mux used at an endpoint, you might see a mux used between a point-to-point pair over fiber. You see an OADM used as part of a ring or somewhere in the middle of a fiber span. So you pass some channels through between, say you have A, B, and C, and you have a mux at B. You pass a signal between A and C without disturbing it, and you drop some other channels into B. Here's kind of a diagram showing that, where channels 1, 3, and 5 are dropped. Channels 2 and 4 are passed through. So you have between your drop, you have channels 1, 3, and 5 coming in from the west side. You have channels 1, 3, and 5 going out to the east side. And you can use you can construct an OADM ring, and you can reuse portions of the frequencies at different parts of the ring, because where you might use it over here in this part of the ring and then drop it, you might reuse it on the other side of the ring. The slightly more advanced variant of that is called the ROADM, which is the reconfigurable optical add-drop multiplexer. It's basically a software tunable, this is generally in software, a tunable OADM, where instead of the hardware being manufactured to only drop a specific channel, you can control, usually in software, which channels you want to drop, and that increases your channel flexibility. So you no longer have to be very precise on what channels you build your OADM, what channels you plan for, what channels you keep in inventory. You get a lot more flexibility. The really cool thing is that modern ROADMs are what's called multi-degree. So in this example, you see what's called a 2-degree OADM. You see a left and a right side. But you can have more. You can have a 3-degree, a 4-degree. And what this is instead of a single drop, you now have a north-facing signal. So you can OADM between do-doot, 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 down, up, left, right. You can do a big star topology. The other optical component that is important is the amplifiers. Amplifiers basically just increase the intensity of a signal, just like any other amplifier. It's a volume control, basically. There's different types of amplifiers for different spectrum of light, but the one that most people are concerned with is called the erbium-doped fiber amplifier, or the EDFA. That's basically what you see in most metro systems. That's what you see in even a lot of long-haul systems. Another major method is called Raman amplification, but you typically see that on like undersea cables or very ultra long-haul systems. So basically I'm just talking about EDFA here. But what you do in an EDFA is there's a piece of fiber that's doped, it's coated with erbium ions. You take your signal in and you have what's called a pump laser. The pump laser works at different frequencies which are not the signal you're trying to transmit, in this case either 980 or 1480. You pump that laser power into the system. That laser power combined with passing through the erbium excites the signal that you're trying to amplify, makes it brighter, and then on the way out you filter out the laser that you just pumped in. And so now you have a much brighter signal than what you started out with. There's a lot of advance in optical switches. Optical switches are basically fancy arrays of little mirrors that let you control the mapping of a signal between particular ports without doing an OEO conversion. You're not going optical to electrical to optical. It's purely a mirror. And basically this is the basis for a lot of other technology. It's the basis for ROADM technology and a lot of other things. There's vendors like AMP6 that use it for optical protection, where if you want to move a fiber from this side to that side, you can flip a switch and it moves the mirror, moves the light. There's a lot of people that use it for patch panels, that kind of thing. So you don't need to be concerned about what media people are passing across. You're purely just passing a light signal, and that's basically how that works. There's a component that most people don't see, but it's actually part of how all these systems tie together. It's called the circulator. So the way the circulator works is it's a device with 3 fiber strands. There's a 1, a 2, and a 3. And the signal that comes in port 1, it sends out port 2. The signal that comes in port 2, it sends out port 3. So here's an example of how an OADM works. There's one of those Bragg grading filters that cuts off or reflects only a specific frequency of light and passes the other through. And so the specific frequency of light that you want to drop gets reflected, it comes back in port 2, and then you drop it out port 3. The frequencies of light that you don't want to filter just go straight through port 2 and passes onto the other side. So that's really how all these systems tie together, is with the circulator. It also it keeps light going one way. There's also splitters and taps. Splitters basically do exactly what you would think they do. They split the signal. Probably the 2 most common examples, you could take a 50-50 splitter, and there's a lot of optical protection that you can engineer using this, where you take your signal and you now cut it in half and send it 2 different directions. And then on the receiving side, you have a very simple optical switch with power monitoring capabilities, and it says which one of these 2 signals is stronger, and it uses that one. And if the signal ever dies, if there's a fiber cut, if there's an issue, it immediately switches over to the other signal. So you get optical protection over your entire spectrum for only a 3 dB hit, losing 50% of your power. It's a very cheap method of protecting a lot of channels, especially if you're using this with WDM. To just optically protect them. The other common example is like a 99-1 splitter. You typically see this integrated into muxes or things like that, where you want to tie in an optical performance monitor. So you might tap 1% of the signal and send it over to a spectrum analyzer, and it knows that it's only getting 1% of the signal, and it adjusts its monitoring accordingly. But you use that to see what channels you're passing, what their power levels are, things like that. Like I said earlier, there's a lot of different types of single mode fiber. The most common are the standard single mode fiber, which is sometimes called non-dispersion shifted fiber. It's under the ITU standard G.652. People call it SMF28. There's low water peak fiber. There's dispersion shifted fiber, there's special low loss fiber, there's non-zero dispersion shifted fiber, and there's bend insensitive fiber. These are basically the main standard types. So standard single mode fiber is the original fiber that was mostly widely deployed, early 90s. It's called SMF-28. SMF-28 is actually a product name from Corning. It just happened to be the fiber at the time that most people deployed. The proper term for it, you can just call it classic, standard, single mode, or you can call it non-dispersion shifted fiber. It's covered by the G652 standard, and it's optimized for 1310. 1310 is where the lowest rate of dispersion occurs. The attenuation rate is lower at 1550, but there's more dispersion. So you're, in this type of fiber, you're basically dispersion limited. Where you go 80 kilometers over this type of fiber, you're now at the amount of dispersion that interferes with optics heavily. So that's basically the limiting factor. They made a type of fiber called low water peak fiber, which, like I said, takes out, in the manufacturing process, takes out some of that water peak and makes a portion of the spectrum usable. There's basically just a graph showing that, but we already talked about that. Then they made what's called dispersion shifted fiber. Basically, this was an attempt to improve the rate of dispersion that occurs at 1550. So like I said, there are different rates of dispersion for different frequencies depending on how the fiber is engineered. And classic SMF, the point of zero dispersion crosses right through the 1310 spectrum. And so they said, wouldn't it be nice if we could engineer fiber where we just shifted that point of zero over to 1550 and then everything would be good. Turns out there's a big problem with doing that. When you run DWDM across the actual point of zero dispersion, there's a lot of what's called nonlinear interactions. And there's a lot of physics that I'm not even going to begin to touch, but a notable example is called four-wave mixing. It's kind of like harmonics of light. You pass three equally spaced wavelengths through, and the light interacts with each other to actually produce a fourth wave. And that fourth wave can interfere with another signal, cause noise, cause problems. So people deployed a lot of this dispersion shifted fiber before they really knew what was going to happen, and then they got themselves into a bind. Like I said, the L band that's used in Japan is specifically to get around that. They deployed a lot of this fiber, and then they found out later that they were screwed. So they actually had to re-engineer their optics around that. So they said, well, the easiest way to work around this is to have dispersion shifted fiber doesn't go down completely to zero. You move the 0 point slightly outside of the band that you want to talk to. So you get less dispersion, but you still get some, and that avoids the nonlinear interactions. So in order to manage dispersion, since now you have these somewhat dispersing fibers, is you have two different types. You have one that disperses the signal where it compresses it, and you have one where it spreads it out. And by running the signal through one and then through the other, you end up kind of back where you started. So there's the two slopes of non-zero dispersion fiber, and that's how you a lot of times deal with dispersion compensation. The other types, there's specific special low attenuation fiber that's used for undersea cables, where maybe you don't care about dispersion so much because you can fix it with dispersion compensating fiber, but you really care about the placement of your undersea amps, because these cost millions of dollars. So it's specifically engineered to be very low dispersion, very low attenuation. And then the newest kind is called bend insensitive fiber, which it's not really insensitive, it's just less sensitive. But it's fiber that's designed for fiber to the home, office building type applications where you don't have the same engineering level that goes into a data center where you engineer your fiber all nice and neat. You have these installers who are used to pulling power cables through just by yanking it. So you need to deal with bend radius that is beyond what you might normally see. Generally speaking, the modern fibers are all better than what the spec says, but also generally speaking, most of the fiber that's in the ground is not modern. It's been there for a while. It's older generation. So here's kind of a graph showing the different rates of dispersion for different types of fiber. So you can see classic fiber up there on the left, the G652. And then there's three major manufacturers that make the non-zero dispersion shifted fiber. You see the zero is shifted well outside of the C band and L band where you want to talk. And different slopes, and you're supposed to engineer your system to match that. So some of the work that goes into actually engineering an optical network. One of the big things you have to concern yourself with is what's called insertion loss. And basically that's the penalty that you pay just for inserting the fiber. It's connector loss, splice loss. It's anytime you run through a mux. The splices and the connectors aren't actually perfect. So every time you run through a patch panel, every time you run through a splice, you're going to take some amount of signal hit. And the typical budgetary figure for a connector is 0.5 dB, and it may be less or it may be more. It depends on what type of fiber you're using, how clean the data center is, how nice the connectors are. You also take insertion loss when going through muxes. So a 32-channel 100 gigahertz DWDM mux, I mean, we have a bunch of these, and by the time you do a mux and a demux, you've actually taken almost the 10 dB hit just to run through the mux. And the reason for that is, like I said, the way the mux is constructed is you're passing through all these different levels of filters, and so the more channels you try to break out, the more channels this has to go through. So there's lots of little insertion losses along the way, and it adds up to a lot of loss. Kind of the three ways that you can screw up the connector process is number one, when you have mismatched cores, like if you plug a single mode into a multi-mode fiber, they're not going to match up. If you have misaligned cores, if you have a fiber connector that's not seated right or whatever, and then if you have an air gap between fiber, that's going to give you a lot of signal attenuation if you don't have the fiber completely seated, if you don't have a clean mating. So in order to plan your network, basically you need to come up with an optical budget. When you buy an optic from a vendor and it says 40 kilometers, that doesn't mean anything. That's a guideline. You can, in some cases, do a lot better. In some cases, you can do a lot worse. So you need to figure out, and here's kind of a diagram showing the way that you do this. You start with a specific transmitter power. You see fiber losses along the way. You see big steep fiber losses when you hit certain connectors or splices. You get down to the end of the link and you need to make sure that you have enough signal left over to stay above your receiver sensitivity, and also not to have a little bit of margin built in, because patch cables do get bent around. The optics transmit less hot over time. If someone cuts your fiber and then the splice people run out and they fix it, they've now added a new splice. Maybe they were in a rush. Maybe you add up impairments over time. So you want to leave some margin built in there. I somehow managed to not get the correct version on here. You can basically Google for optical budgets, and you can find a bunch of different websites that show kind of the values that you use. But basically, a fusion splice, an actual manufactured fusion splice, the amount of loss is so low as to almost be negligible. The problem is most people are not doing nice factory-made fusion splices. When you get out in the field, when you run a cross connect and there's a tech out there field terminating it, and they're doing it with a little kit, and they're using pre-done connectors, and they're just cleaving it and trying to line it up just right, you might see a lot more loss. So you kind of got a budget for more of that. And there's different loss rates for different types of fiber at different bandwidths and different frequencies, and you can find this online. So when you work with amplifiers, there's actually a lot of work that goes into maintaining the power balance, because amplifier gain is not perfectly flat. You have some portions of spectrum where you get more gain than others. And if you didn't equalize this, what would happen is kind of in the diagram below, you see over time, over the course of several amplifications, you have one channel that ends up getting much stronger than another channel. And when you have channels that are not equalized like this, it causes a lot of noise issues. So you really want to try to engineer your network to keep these flat. So what happens in the amplifiers is after they get done amplifying, they run through a little filter that kind of brings all the signal levels back down to the same level. You need to take care when you're with an OADM system where you have one channel that may have come from 40 kilometers away and you have a new channel that's coming locally. You're going to have very different power levels then. So you need to take care to design your network. A lot of times what ends up happening is you have to actually attenuate your signal. which then means immediately at some point you're going to have to amplify it again. But there's a lot of, this is what goes on in engineering a complex fiber network: attenuate, amplify, to get all these parameters exactly right. There's a lot of stages that you go through. There's another problem with amplifiers and total system power. So what people don't typically realize is, say for example you have a single DWDM channel and it's doing 10 dBm, which is 0.1 milliwatts of power. Now you grow that system over time to a point where you're now carrying 40 channels. Each one of those channels carries its own power, so the total system power is now up to 4 milliwatts of power, which is 6 dBm. That's, you know, a 16 dB difference, which is pretty big. So the amplifiers actually have, there's a minimum amount of power and a maximum amount of power that they can take, because if you start with too strong a signal and you try to amplify it, number one, there's a limit to how much signal you can put across the fiber before you start causing more nonlinear interactions. And number two, there's a limit to the engineering of the amplifier, right? So you want to start out with a signal that's low but not too low, and then amplify it to a signal that's high. You don't want to start out with a really high signal. So your amplifier, a typical input maximum, may be minus 6 dBm total power. So if you have 40 channels, that means that each channel before you amplify it needs to be minus 22 dBm, which is pretty low. You have to really take this into account when you engineer a complex amplified system. And also remember that the total input power can actually change when you lose a channel. So say for example you have a 40 channel system and 20 of them are in a pot that loses power. Boom, you just lost a whole bunch of optical power in your system. So what happens is people engineer the amplifiers to do dynamic gain to maintain a working system level. But there's a lot of, it's a lot more than just amplifying the signal. You need to kind of engineer it to keep it within these constraints. To deal with dispersion fiber, like I said, there's different types of fiber. There's fiber with a positive slope, fiber with a negative slope. And basically, what happens is you end up using one type of fiber in your deployment, and then you use the other type of fiber in what's called a dispersion compensation unit. It's basically just a box with a big spool of fiber in it. And you run your signal through it, and it disperses it the other direction. It counteracts the dispersion that you encountered when you actually ran it across the long haul. And typically, they use circulators to give this a second shot, so you may run the signal through the fiber twice to use less fiber and accomplish the same amount of dispersion compensation. But basically, that's all these things are inside. They're boxes with a bunch of fiber in them, and they may charge you thousands of dollars for them, but this is all they are. The other method people use to deal with dispersion that's becoming a lot more popular is electronic dispersion compensation. And basically what's been happening is over the years the technology has been getting better and better to the point that electronic dispersion compensation is being integrated into the pluggable optics. And it's basically what's responsible for the modern generation optics, where you can run a 10 gig fiber over a 10 gig signal over a multimode fiber with LRM. That's basically because of electronic dispersion compensation. And the technology is getting better, the silicon's getting better, and that's basically going to be very essential in the future 40 gig and 100 gig technologies. Another concept you have to deal with is regeneration. There's three types of regeneration that people are concerned with, and they're called 1R, 2R, and 3R. The first 1R is re-amplifying. Basically, this is purely what an amplifier does. It makes the signal stronger, makes the light brighter. It doesn't do anything about reshaping the signal. That's a 2R regeneration, where what happens is you want to restore the signal back to its original shape so that it's easier to tell when it's a 1, when it's a 0. And then 3R is retiming. It's restoring the original distances between the pulses, because these distances change over the course of a long transmission. And basically, you can perform 1R and 2R. You can even do some amount of 2R in an amplifier. But to do a full 3R pretty much requires an OEO conversion. You take two optics and you go from an optical signal to electrical, back to optical. You now have a completely clean signal that's completely regenerated. Another concept people talk about, it's not that important in understanding what you're doing, but basically there's a concept called an eye diagram, which is just like an oscilloscope view of a digital signal. And what you're looking for in terms of a quality signal is the eye opening, the big opening where this plus is here. You want that to be clear so that you can distinguish whether it's a 1 or a 0. And the image on the right shows what happens after you have a heavily distorted signal that you can no longer tell what that is. You'll see people talk about that as far as like evaluating the quality of optics. But so what happens when you have all these impairments and they start to do bad things is you get bit error rates. So what happens is the signal doesn't actually just outright die. You don't cross a magic boundary where all of a sudden you had a perfectly working signal and now you have a dead signal. What happens is as the signal gets worse and worse and worse, the bit error rate gets higher and higher. So when you get to the point where your optic can no longer receive beyond a certain point, you might be able to get 1 dB past that, but you also increase your bit error rate by a power of 10. And as you go down more and more and more, the bit error rate gets higher and higher, usually by powers of 10, to the point where you have no signal at all. And that's where forward error correction really makes a big improvement. Is at a point where you might have had a really hideous bit error rate, you're able to compensate for that with FEC. And that lets you get a lot more receive sensitivity out of the whole system. I wanted to talk about the tools of the trade people use. The most basic is the optical power meter, which is the technical name. People just call it light meter. Basically, it just measures the brightness of the optical signal. What you want to see in terms of measuring an absolute signal is a dBm or a milliwatt value. What happens, though, is most light meters actually include, it's not just a light meter, it's also a cable tester. And so when you're using it in cable test function, what happens is you switch it to dB mode, not dBm mode. You're looking for relative loss. You start with a known transmitter on the other end, and then you look to see how much the signal has changed, and you use that to test your cable. And that's completely different than seeing how much light am I actually seeing. And I've had a horrible experience with data center techs that just no one knows how to do this correctly. So if I had a nickel for every time someone told me they just measured some signal that should be blinding them, I'd be very rich. So when you work with light meters, really keep that in mind. Make sure you're looking at the right mode. But basically, these are a couple $100 devices. So if you do any work with fiber, get one. Get one on eBay. Get one new. Doesn't matter. They're not that expensive, and they're really essential to doing any kind of troubleshooting. The next big one that people use is the OTDR, the Optical Time Domain Reflectometer. And the way this works is it injects a pulse into the fiber strand, and it doesn't even need the signal to come back to it. Basically, what happens is there's certain properties inside the fiber where the light gets scattered, and some of the light will be reflected back to you. And by timing how that return comes back to you from the different pulses that you send, you can characterize the fiber. You can see the splice points, you can see the overall length of the fiber, you can see the overall fiber attenuation, and you basically use this to tell where there's a break. You stick it at the end and you say, 62.4 kilometers that way, there's a break. And here's kind of a Wikipedia example of an OTDR. Here's an example output of an OTDR from some fiber that I have. And you see the major splice points. You see where the signal changes. And basically what it's looking for is it's looking for events. So it says 2.3 kilometers out there was this event, 6.8 kilometers. It's identifying where all the splice points are because it sees the increase in reflection, the increase in loss, and it can tell you where there's a really dirty splice. Like in here you see there's a splice where there's like a 1 dB loss. Which is much higher than you would really want compared to a splice which is 0.06 dB loss, which is a well-engineered splice. So I wanted to kind of get into the questions that people frequently ask, kind of the urban legends and myths surrounding optical networking. And one of the big ones is, can I blind myself by looking into the fiber? To which this picture always comes up immediately, which is, do not look into beam with remaining eye. So to understand laser safety, you have to understand there's 4 safety classes that the lasers are grouped into. Class 1 is completely harmless. Either it's low powered enough that even if you stared at it for the rest of your life, it couldn't do anything to you, or it's inaccessible in operation. So like your DVD player, for example, you can't get at the laser while you're playing the disc, and when you open it, the laser goes off. So it's a class 1 laser. It's safe in normal operation. A class 1M is the same thing, but don't look at it in a microscope. That might focus the light, amplify it enough that it now causes a problem. Class 2 is basically only harmful if you stare at it. So this basically covers ordinary laser pointers, supermarket scanners. The theory here is if you don't want to blind yourself, you should go, hey, stop shining that at me. If you do want to blind yourself, you can stick it up to your eye for 10 minutes and it will cause damage. You can do the same thing by looking at the sun. You have to intentionally want to cause damage. The class 3 laser, you get into where you don't want to view them directly at all, because either they might cause damage by a reflection in the case of a 3B, or they might cause damage even if you just briefly shine it at your eye for not minutes at a time. So inside a 3A, there's an old system and a new system. This got changed like 10 years ago to kind of better address the way laser safety really works. But there's a distinction in class 3 between systems that are high power but still not that dangerous, and systems that are really, really dangerous. So when you cross into a class 3B laser, basically a 3A can be between 1 to 5 milliwatts of power. A class 3B goes all the way up to 500 milliwatts, so there's a huge jump. Basically, a class 3B system, in order to be legal, there has to be a key, there has to be a safety interlock system. That's why the crazy internet laser pointers that you find, they're all illegal. They all get seized because they don't have those kind of safety interlock systems. So if Avi's around somewhere and he has his green laser pointer, don't look at it. And then you get into class 4, which is basically chemical lasers, and you know a class 4 because it's going to burn you, melt you, set things on fire, cut steel. Generally not used in telecommunications. Networking lasers all operate in the infrared spectrum. Infrared can also be classified into different bands. There's what's called near infrared, which is between 700 to 1400 nanometers, and there's far infrared. And one of the reasons behind the 1310, 1550 split is near infrared is actually a lot more dangerous than far infrared. What happens is the human eye is not meant to see infrared, and so it does a very good job of blocking the signal. When you get into what's called the IRB spectrum, your eye basically blocks all that light out. So the safety, you might have a laser that transmits 10 milliwatts of power, but the amount of power that can actually physically make it through your eye brings it down into a class 1 system. So that's where you see all the really high power lasers really are in the 1550 spectrum, and that's into the shortwave infrared band. So basically what it comes down to is I have not been able to find a single router port, be it built-in, integrated, pluggable, of any kind, doesn't matter what the reach, doesn't matter what the power, I've not found anything that is not a class 1 laser. There's no router you can walk up to, look into, that can hurt you at all, period, the end of story. What can start to hurt you is when you have optical amplifiers, especially long-haul systems, but even a metro system is capable of putting out enough power that it now officially falls into the 3B category. So don't look into optical amplifiers. And the other thing is don't look into the common fiber, because like I said, if you have what might be a very low-powered system times 40 now becomes a very high-powered system. So generally speaking, if you don't know, don't look. In reality is you can't see it anyways because it's infrared. But the question comes up, should I be wearing my safety goggles to the colo? Generally speaking, the answer is no, because direct router ports are low power devices. Even on DWDM systems, it's not like you're sticking the fiber right to your eye, right? You might glance at it accidentally at an angle through a lot of air. Once the signal goes through air, it really disperses quite a bit. So there's not huge safety concerns. Like I said, wavelengths above 1400 are IRB, and they're mostly blocked, so there's a much lower level of light that can actually get into the eye. And then the really high-powered systems all have safety mechanisms. So what they might do is they might send an auto-negotiation signal that lasts 10 nanoseconds, and if they don't get that signal back, then they turn off the laser. And that's what you see in ultra-long-haul systems, submarine systems. There's safety mechanisms built into this so people don't go around blinding themselves. So people ask, can I even see the light at all? Like I said, no. The human eye can only see between 390 to 750. But a lot of people say, well, I looked at an SX fiber and I saw red. Well, what you're actually seeing is the sidebands, because the signal generation is not perfect. The light spectrum is not entirely confined to 850. There's these little sidebands that spill over, and so you get a little bit of signal that spills over into red that you can see, and now you can look down this multimode fiber and you can see a little bit of red. Kind of a cool trick if you want to see if a fiber has signal or not is you can use a digital camera because they are sensitive to infrared. So here's an example of a digital camera taking a picture of a remote control, and you can see the light. So if you've got a camera phone, you can hold it up to your fiber and you can actually see light coming out of there. It's a quick and dirty trick to see if there's signal. The next question I get asked a lot is, can I actually damage my transceivers by overpowering them? Can I send such a strong signal that it burns out the optics? Yes and no. It's not actually the overpowered transmitter that causes the problem, it's the sensitive receiver. So on a typical, the difference between a 10 kilometer and a 30 kilometer optic, the difference in output power typically is going to be about 3 dB. It's not that much. The way long-reach optics works is they have very sensitive receivers. So an 80 kilometer optic may have a 10 dB or more sensitive receiver than a 10 kilometer optic. And it's the sensitive receiver that is in danger of burning out. So there's basically two threshold points that you actually care about. One is the saturation point. That's where the receiver's blinded. You can actually send a signal that's so strong that it doesn't cause any damage, but it can't be read, and so it just causes bit errors. And then you get to a point that's actually the damage point where you can actually burn out the receiver. It depends on specific optics, but I kind of went through some vendors and pulled out some kind of standard ranges. And basically what I'm showing here is the difference between a 10 kilometer, a 40 kilometer, and 80 kilometer optic. The red shows the range of values that are acceptable for transmit. So even though you could get all the way down to like a -7 signal out of an LR and still be acceptable, for the most part you're going to see about -1, -2, -3. And the things that are on the very low end are maybe 10% of what they ship. But they have what's called an optical budget, which is the difference between the lowest that they will ever ship a transmitter and the lowest that it can receive a signal. And the difference between the two is where they set the 10 kilometers. But if you happen to have an LR that performs much better than the minimum spec, kind of like overclocking your CPU, you can get much longer distances. And I've actually seen people get 22, 25 kilometers out of a 10 kilometer optic just fine without any amplification or anything. But the kind of red and blue dotted lines are the red's the receiver damage threshold and the blue's the blindness threshold. And so you see in a 10 kilometer optic, the maximum that they will ever ship an optic doesn't even fall into the blindness threshold. So that's where you can always use an LR optic you can use LR within the same rack over a 1-foot patch cable and it'll work. When you get into ER, you're now getting into ranges where it won't work if you're directly connected. The receiver blindness threshold is now below what the optic is going to transmit. So if you've got ER within the same rack, you're going to need to attenuate or pad it. But the blindness, the damage threshold is still above what it's ever going to transmit. And then, like I said, when you get into the long reach optics, what's happening, you see the huge difference in receive sensitivity. Because this receiver is now more sensitive, it's more susceptible to damage. And so the damage threshold is now moved down not into what it might transmit, but even below what it might transmit. So that's where if you're doing things that are like below 20 kilometers, things like that, you still need to pad these 80 kilometer optics to prevent damage. But it's really a function of the receiver, not the transmitter. So people keep that in mind. Question I hear a lot is, do I really need to be concerned about bend radius, or is this some weird telco thing where people are all, is this like, I should always have my static strap on before I touch my router? Who does that? No one. The reality is, yeah, bend radius is actually a real issue. Remember, the way that total internal reflection works is the light has to hit the fiber at a certain critical angle. And if you bend the fiber beyond that critical angle, the light actually leaks out the side. And kind of a cool thing is they make light meters that clamp onto the fiber. And they bend it a little bit, and they detect the light that comes through all the plastic and everything, and they can actually give you a light meter reading. They cost a couple $1,000s, but they're kind of cool. So they make bend-insensitive fiber for residential office use, things like that. But the thing to keep in mind is you have to trade some kind of performance for that. You give up, low attenuation or something. So you don't really see that in the data center. So if you go take your fiber in the data center and you bend it, yeah, you can look on your light meter, you can see the signal go down as you do that. Another question that I hear a lot is, can two transceivers on different wavelengths talk to each other? And that's another yes and no question. Between the right type of optics, yes. The way this works is all optical receivers, for the most part, every example that I can find, are wideband. There's a difference between like an LED transmitter and a laser. So you can't make an old SX fiber or a FIDI fiber talk to something 80 kilometer. But within the 1260 to 1620 range, all of the receivers are the exact same unit. Doesn't matter what DWDM, not DWDM, it doesn't matter what you put where. They're all seeing the entire spectrum. And so there's no reason that you have to make two fibers transmit to each other over exactly the same spectrum. And there's a lot of DWDM networks that are built around this, where you have mismatched wavelengths. You have one wavelength going this direction, you have another wavelength going this direction, and you run over a single strand of fiber. And there's actually a little bit of redundancy you can get built into that, where it has happened where, or actually it happens quite a bit, where we have one fiber go bad and the other fiber doesn't. And so you may not lose your entire capacity, you may only lose half if you engineer your network this way. The downside is it's a little confusing for techs, and they're like, spaghetti mess, where does this cable go? The only gotcha when you do this is that the power meters will be slightly wrong. So what happens is when you use a power meter, it's calibrated like you use a power meter and there's a button that says 1310, there's a button that says 1550. What that's doing is it's changing the internal calibration. So if it sees light and you're telling it that the light it's going to see is 1310, it might tell you that it's a minus 15. And if the light that it's actually receiving is a 1550, it might actually be a minus 14. And so if you don't have the receiver set to, if you're using like integrated DOM, things like that, the value is going to be slightly off. And it's not off by a lot, but it's off by a little bit, just because it's expecting to see 1310 and it's actually receiving 1550. It still sees the signal just fine. So obscure optical networking trick here. You actually don't need to have two long reach optics paired with each other to get long reaches. So say for example you're comparing an LR which transmits at 1310 and is 10 kilometers. You're pairing that with a 1550 that is spec'd for 40 kilometers. What happens is the 1550, the signal has a much lower rate of attenuation. So like I said, typically it's not quite half, but it's pretty close. So the signal is going to degrade, it's going to attenuate a lot less by the time it reaches you. So the LR side is going to be receiving a stronger signal. On the other side, the ER optic has a greater sensitivity than the LR. So you combine these two things and you can actually get 40 kilometer reaches by mismatching an LR and an ER. You don't need two 40 kilometer optics. And this is, of course, dependent on the actual engineering of your system, and you need to check before you do this, but people have been using this trick for a while and it works. Another question is, do I really need to clean the fiber? This is, vendor excuse number 738. We cleaned the fiber and it fixed it. And you go, do I need to send you guys some Windex? You have a lot of dirty glass. Yeah, actually, the fiber does get dirty. There's a much more detailed presentation that you can go read if you want to kind of see how the microscopes work and how to do the cleaning of the fiber. But there's an example where you see a really dirty connector at number 3, and that's just grime and dust and dirt in the colo. It gets in the way, it blocks the signal, and it can actually damage the connector to the point where you have to throw it away. If you have a piece of dirt in there and you kind of get it embedded in the mating, it might actually damage the glass physically. Other miscellaneous fiber information. I have people ask me, how fast does light travel through fiber? If you want to do the calculation, the speed of light is about 300 million meters per second. SMF-28 core has a refractive index of 1.468, so what you do is you take the speed of light, you divide it by the refractive index, and now you get the speed that the light travels in fiber. And if you translate that out to milliseconds, for every 200 kilometers or every 125 miles, you're gonna see 1 millisecond of time spent. And if you want to kind of compare that to what you see in a trace route or a ping, you cut that in half to account for round trip time. And now you can say, for 100 kilometers of fiber, I should expect to see 1 millisecond of delay due to the speed of light transmission. People say, well, how come I see much higher values in real life? The reality is they don't lay fiber in straight lines. They lay it all over the place. They go in rings. They have big dispersion compensating spools. They go through all these patch panels and back and forth across the data center. I've seen 2 kilometers worth of fiber go into trying to get out of 111/8 in New York. Just by the time you go through all the different patch panel facilities that you need to go through. And then a little talk about the future of optical technology. Right now, the system that most optics use is a really simple system called non-return to zero. And basically, it's a glorified version of Morse code with light. You turn the light on, you turn the light off, and you do it really fast, and that's how you get your signal. But there's actually better modulation techniques that are available, and these are being adopted right now, and they're actually the basis for a lot of what's going into the 40 gig optical technology that makes it work as well as 10 gig does today. We kind of hit a point where we can't signal any faster, but what we can do is we can carry more data per signal. So different techniques like dual binary, DPSK, DQPSK, you can encode 2 or 4 bits per symbol. And there's really complex, there's a half dozen different methods out there, but you can encode a lot of data. You can do phase encoding, you can do modulation encoding. There's a lot of stuff out there. And this kind of shows the benefit. Here's a 25 gigahertz filter showing you're encoding you're encoding more data in the same amount of spectrum, up to 22 gigabits per second in a dual binary. You go all the way up to 44 in a DQPSK. So this is basically the basis of the technology that makes 40 gig optical work outside of very short reaches. So you can now do long haul 40 gig. Basically all the existing systems out there are based around, they're using dual binary, they're using DPSK, they're using something like this. And then another topic that comes up is alien wavelengths. So normally what happens, for some definition of normally, is a DWDM system is run by a single entity. Say I run a DWDM system. I control the fiber, I control the channels, I control what goes into the system, I do the engineering. And when I want to hand off to a customer, say I want to hand off a signal to Patrick, I've got to convert that back to a standard gray optic, a 1310 to 1550, a standard signal. Then he takes it and then he does something with it. And the conversion layer actually adds a fair amount of overhead to the process and cost and inefficiencies. So people ask, what would happen if I were to just talk to my customer with DWDM? What if they had a DWDM tuned optic and they sent me a signal and I stuck it straight into my Mux? What would happen? And this concept is called alien wavelengths. The biggest problem with it is that without having that layer of conversion, I no longer have control. I don't know what Patrick's sending me. As we discussed under amplifier management, if he starts sending a wildly high or low signal it might not work. And so I no longer have visibility into that or control over that. And he could potentially end up sending me light that's so strong that it harms other systems, particularly if it goes through an amplifier. You can kind of make the argument that if you don't go through an amplified system, you can get away with this. So what I expect to see more people doing in the future is, instead of selling dark fiber, they sell a wavelength slice over a dark fiber. So you might take your one dark fiber, turn it into 40, and now sell individual wavelengths to individual people. The concept is getting more and more popular as more and more end user customers have DWDM tuned optics, but it's not there yet. There's still a lot of limitations. And that is basically it. Questions? Microphone.
Regarding amplification, I've got a few LRs that just are a few dB lower than I really need them at. Is there a simple 1310 LR amplifier that's not going to cost more than the whole caboodle? We can talk vendors offline, but if there's something that you can say, hey, this is a good option.
There's not, and the reason for that, like I said, EDFA works across a certain frequency spectrum, and 1310 is outside of that. So there's no, I'm sure there's probably somewhere some amplification system that works, but there's no commercial system that anyone uses. Yeah, basically that's a limitation that you hit, and that's where you get into those kind of situations where you might make the other side have a stronger receiver to work around that, or even if you have some, you might just do the optic shuffle. You might test, and then find two that are stronger than the rest and use those.
So I'm already muxing 1550 and 1310, so I can't just use the ER-LR mix. Does anybody rent OTDRs that I could point the finger at the right vendor and be like, no, it's your cross-connect that's breaking me?
What I do in that situation is I call AboveNet and I tell them it's their fault, and they've sent someone out with an OTDR and they test it, and then they tell them that it's Equinix's fault. Yeah.
Then it's just constant finger pointing. Like, is there a simple OTDR, like USB OTDR?
No. There's OTDRs on eBay, but you're going to be looking at several $1,000s, which is better than the new cost, which is several tens of thousands of dollars. But no, there's no.
Does anybody own one in the LA area and would like some beer?
No, literally what I do is I work with the actual fiber vendor, because they have one and they have a guy that'll come out and test it, and you say, you're having a problem with this fiber, and they'll send someone out and test it.
Try working with LA DWP, it's tough. So.
Well, different problem there.
Yep. Yeah, our outside plant guys are telling us we have to move to angled polish connectors, and we're concerned about the mismatch between that and the UPC on all the Ethernet transceivers we use, having to come out with the right cable type and all the different permutations. Do you have any take on that? What do you think?
I had some slides on that, and I kind of cut them for space. So there's different types of connectors. I didn't have time to really get into like all the different types of connectors out there, but what he's talking about is like an SC connector that you might see that has a blue end. That's what's called a regular polish connector. You might see a green connector. That's what's called an angle polish connector. What happens is, instead of being perfectly flat, it's at like an 8-degree angle. And when you mate these two, it reduces the amount of reflections that you get. The problem there being you've got to manage all these different patch cables, and finding angle polish connectors are kind of difficult to do. Realistically, what I've seen is the need for it is not actually as great as people say it is. It depends on your specific level of engineering, but if you're kind of building an IP network and you're doing a little WDM, you don't need to be concerned about it. If you're a cable operator, maybe you do. Yeah, there's going to be some expense in buying the angle polish connectors. Make sure people don't mismatch them, because when you do that, then you get an air gap, and then you get lots of problems. So yeah, there's a lot of work that goes into that. Anybody else, or have I bored you all sufficiently? All right.